Okay, we should be live in a second.
Okay.
I think we are already. Let me check. Okay, I think we are already there.
All right. Do we want to give?
Maybe we should expect now that many people is joining the YouTube, because for now I am the only one in YouTube.
Okay. Well, that's not off to a good start. Is it possible that everybody's on the old link?
No, I didn't change the link.
Oh, okay. You
Eventually.
managed to make it work then.
Yeah, because when I came back home, I did some new test, and the same message appeared, and then looking for some solution in the web, someone said, "Oh, you had to change the priority of the process and so forth." I also decreased the resolution of the video. Well, let's hope that this is enough.
Okay.
I will see. If you don't mind, I will make first an announcement of Scala Days, or maybe you would like to do it yourself. You are in the program committee. If you want, you can mention. I can open a you can open a tab in your browser and say something.
I mean, it's your event, so you should be the one to announce it.
Okay, perfect.
But I'm happy to say that I'm on the committee if you want.
Perfect. Yeah, no, that's okay.
Are we live now? Because I don't think I'm allowed to talk about the reviews on your
Sure.
I'm not allowed to, but I will offline.
No, that's okay. Okay, let me check in the mobile phone. So we have a chat.
Yeah,
Hi, anybody there?
So apparently you have to be signed in to be allowed to post on a chat. So maybe there are people who are logged in, but anonymously.
No, Camilo Casas. I don't know this guy, but hi, Camilo. And Javier is fearful from your talk. Do you have? Maybe you could open the YouTube link and also see the chat. Maybe if you like.
I can absolutely open. You mean on Twitter? Yeah, sure.
No, not in Twitter. The chat in YouTube.
What did you want me to share in the chat in YouTube? Sorry.
No, that maybe you can open the YouTube link of the talk.
Oh no, I haven't. So that's what I'm saying.
So you are seeing the messages.
Yeah,
Okay.
and I'm seeing Xavier. Xavier is a friend of mine who just sent me a message telling me I'm not going to be here tonight, and now he is. So
Okay.
he's a weird person.
So maybe it's 7 o'clock now, but maybe we can wait some more time.
We can give it a few minutes, absolutely.
Yeah.
This is your show, so whenever you want to get started, you do the introductions, and then I'll get going.
Okay.
Because you're the boss.
So this is your first time that you deliver this talk, no?
It is the very first time I give this talk. I mean,
It's a new presentation.
I've given it plenty of times to my wall and to my screen, but you're going to be the first living persons to actually hear this talk. I don't know if it's good. I hope it's good. And the point is, you should let me know at the end whether you enjoyed it or not.
Sure. There were 50 people in the meetup.
I've seen that, yes.
Register.
And we're what at the moment? 9 people.
9 people, yeah. Hi, everybody. So for the moment, the connection is
Holding up.
Is holding up.
So yeah, while I give the presentation, I'm not going to be able to see the chat because I'm going to be looking at my slides.
Yeah,
so
sure. Yeah.
Any issue, if the voice gets desynchronized, if my screen doesn't update, let me know.
Yeah. Sure. Javier is provoking you. GADTs in Scala 2 are phantom types, but not GADTs.
I'm sorry.
It's a comment from Javier.
Yeah, so the thing to know about Javier's comments is you should mostly ignore them because he's going to try to say complicated stuff to get me to mess up. He comes to every single one of my talks and tries to get me to mess up. He's a good friend, but we have a peculiar kind of relationship. So, ignore him. He's probably best for everybody.
Okay. If you want, we can invite it to the Google Meet. Or better not.
No, let's not do that. No.
Okay.
It's 5 past, 10 people. I think we can start whenever you want.
Okay, but let's start. Thank you very much. Nicolas or Nicolas? Nicolas.
Depending on which language you're saying it. French people would say Nicolas.
Nicolas. Okay,
yeah.
Nicolas. Thank you very much for presenting in our meetup. We have done previously some online meetups, but since the pandemic we stopped doing that, and we like doing it in presence and having some beers afterwards. But this is of course better than nothing, and being able to have you here for us is a pleasure. So
I'd have loved to come and give it in, physically.
Yeah.
That would have been so much better. I love Madrid, but it was a little bit complicated.
As I said, this is better than not being able to enjoy your talk. So before we start, I like to remind you that Scala Days is coming to Madrid. Okay. and well, you are more than welcome to come here, enjoy the city, and say hi. Okay, early bird tickets are already in sale, so please do consider the possibility of join us here in Madrid. And without further ado, please, Nicola, the floor is yours. Thank you very much.
So about Scala Days, quickly, let me plug that in, because I'm on the program committee, so I actually know which talks are going to be there, and you should come. It's going to be a good conference. It's going to be quite good. So definitely, if you can afford it, if you can make the time, come to Madrid. It's going to be a good one. Right, on to the talk. Right, so tonight I want to talk to you about categorical abstractions. Not because it's a very original subject, tutorials on monads are a dime a dozen, but because, well, if I'm being completely honest, there's a conference in Warsaw in a few weeks, and I've never been to Warsaw, and I really wanted to get there. And really, in a Scala community, submitting a talk about monads is basically a surefire way of getting accepted. So the entire point was to get accepted to that conference, and things seem to be working according to plan so far. But of course, that means that I now need to figure out what to say about it, which is what we're doing here tonight. This is a talk I've prepared. I found something that I think is interesting. I've not given it to a human being yet. I've given it to my screen quite a bit, and he seems to enjoy it. But I'd really like proper human beings to have a look before I actually go on stage and give it to dozens of people. So the entire purpose here is you're seeing the first version of that talk, warts and all, and I would really enjoy it. I would really like it if at the end of the talk you could let me know what worked and what didn't, what you liked, what you didn't like, what made sense or what didn't. You're really doing me a favor being here, because I really, really am looking for feedback. Right, so then, the things I want to say about monads and stuff. Well, as I said, it's not a very original subject. So there's been hundreds of talks, articles, tutorials on the matter. So I did my research, looked at what had been done, and came to the conclusion that there's basically two big categories of ways of talking about these things: the really theoretical one and the really practical one. The really theoretical one goes something like this, usually. We explain what the type constructor is, then we say under certain constraints it becomes a functor, and then with further constraints we have an apply, and then with an elec we get an applicative or a flat map, and if we have both, then we have a monad. And by the end of such a talk, usually you have a good intuition of what these things are, where they come from, and what their use case is. But it's not very practical. You don't have any concrete example. So you have built intuition, but you don't actually know how to use them. So you have the complete opposite talk then, which is the one that's really heavy in examples, which usually goes something like that. Well, a type constructor is like a list, right? A list is a good example of a type constructor. And the list is also a functor. It's also absolutely everything else. And that's a problem, because you'll get a few other examples. Option, say, it's a type constructor, that is a functor, but also absolutely everything else. Maybe you're going to get a few other examples. Right bias either, or some things that are a little bit more esoteric, like functions. All those things are type constructors that happen to be functors, but also absolutely everything else. And the fact that all of the data types we usually work with tend to be absolutely all of the abstractions make it really very hard to see the subtle distinctions that exist between these abstractions. So what I've decided to talk about tonight was I wanted to try and find data types that are some abstractions, but not other abstractions. So things that are things, but not other things. And I tried to prepare that in a way that at least I found entertaining, because most of the time when you watch presentations online, it's about people building things. I'm an engineer, which means I like breaking things at least as much as I like building them. So what we're going to do now is try to find what these abstractions are and the least amount of things we can remove and break some things in interesting ways. And the first thing we're going to tackle is something that is not a functor. So the first thing we need to talk about is the notion of type constructor. I do not know whether everybody's familiar with the concept, so I'm just going to quickly explain it just to make sure we're all on the same page. The type constructor is, well, it's a function at the type level. So to take an example, list is not a type. List of int is a type. List of string is a type, right? But you can't manipulate something of type list. That does not exist. List is something that takes a parameter, say int, to produce a concrete type. So that's really what we mean when we say type constructor. It's something that takes a type as a parameter to produce a type, such as list, option, either, all these things. And we want to find an example of a type constructor that is not a functor, which means this is going to be a little bit hand-wavy in the definitions. I'm going to say here, a functor is something that has a map function. So we want something that does not have a map function. What is map? Well, in a context, imagine that you have an f of a, where f is some type constructor. You have an f of a, and you want to get to an f of b, and in order to go from one to the other, all you have is a function from a to b. Well, this is where map comes in handy, because you can use it to lift f and get the function map of f, which goes from f of a to f of b, which is very useful when you want to work with the value that is inside of some f. So now we need to find an example of that works and that we can break. And I mentioned it earlier in the introduction, that function, for example, was a functor. So we're going to look at that. We're going to use a type constructor that is a function from x to a. And in the rest of this talk, whenever I mention a type x, that means some concrete type. I don't care which type, just might be int, might be string, it's irrelevant. It's just a concrete type, sorry. And if you look at the diagram, it looks a little bit different from what we had before, but it's really the same diagram specialized to functions. So we still have our f of a, which is a function from x to a, and we have a function from a to b, and we're trying to get to an f of b, which really means we're trying to draw an arrow from the x to the b. And that's fairly easy to do, right? We just follow the arrows that we have. We just compose f of a with f. Or in terms of code, we do f of a followed by f. And that gives us an implementation of map that works for a function from x to a. Why does it work? It works because our two arrows, f of a and f, compose, right? One ends in a and the other begins in a, so you can do one and then the other. So one way of breaking that, of making it not work, is to say, take the arrow and flip it. And now we're working with a function from a to x and not from x to a. We just taken the arrow and turn it around. And with that, it's no longer possible to compose f of a and f. And so there is no way to get from b to x like we'd want. And so there's no way of implementing map, which means we have found a type constructor that was not a functor, for which we could not implement map. Now, it's not necessarily a very obvious type, so what I like to do is to make the x concrete and give a name to the f to make things more understandable. So here we could say that x is, for example, Boolean, which will mean that f is a function from a to Boolean, which is also known as a predicate. So there we have it. As a warm-up, we found an example of a type constructor that was not a functor, predicate. Well, we've not learned much yet, but we learned something. We've learned that a function parameterized on its output type is always a functor, and on its input type is not a functor. So I don't have access to the chat right now because I'm doing the talk, but I suspect there's at least one person, Javier, who's complaining that a function parameterized on its input type is some kind of functor, which is pedantically true, but not the purpose of this talk. So we're going to leave it at that. Before I continue, do we have any question? I'm going to take that as a no. You can hear me, right?
Not question for the moment in the chat. I didn't mention that in these key takeaways slides, it is a good moment, okay, for asking questions. So
Right. Across the top, there's going to be a bunch of slides like that where I just summarize what we've seen so far. So
okay.
if you have questions, these are the right moments to ask the questions.
Yeah.
Which might be a little bit hard because I think the stream has a delay of a few seconds, but we'll try to make it work.
Okay, there is a guy in the chat who is proud that he anticipated the predicate example. So
Okay.
this is a good example, by the way. So
Cool.
let's go on.
Well, actually, we have all the time in the we have all the time in the world. So let me quickly check the chat. He's always here. Okay. Well, this is not scary at all. Anyway, let's keep going. All right. Now that we've seen
Sorry, Nicola.
Yes.
There is a question. Is there another example of type constructor which is not contravariant, but at the same time is not a functor? Because
well, there's plenty of other examples than predicate, but I do not know any other example than functions parameterized on their input type. There might be. Just because I don't know them doesn't mean they're not there. But the only example of a data type that is not a functor that I know is a function parameterized on its input type.
Yeah. Okay.
Now, the person who asks that is exactly the right kind of person to answer that question. He's also another of my weird friends, and he, if there are, he knows them, and he'll probably place them in the chat. I don't know them.
Okay. Thank you.
All right. Let's carry on. Before we start doing other examples, I need to take a few minutes to talk about product types. Now, I don't know if everybody's aware of what a product type is or familiar with the word, but you're very likely to be familiar with records or structs, or in Scala case classes, which is basically when you take multiple types, multiple values, and put them in a single type. And here, I'm going to use that. I'm going to use this type here. Product of A and B, which is an A associated with a B. I'm going to be using that because it's going to be the basis of all the other examples we're going to find. Now, what's interesting about, two things to know, sorry, about this product that I created, is that first, we have something called product introduction, which means that whenever we have an A and a B, we can always get an A and B through product introduction. And the converse is true as well. Whenever we have an A and B, we can always get an A and a B by product elimination. And with these two rules, that's going to allow us to see quite a few things in the diagram that I'm going to show next. So for example, I want to prove that all such products are functors. If we take f here to be a type parameter A and some concrete type x, then it's always going to be a functor. So let's try to implement map. We have a function from A to B, and we start from an f of A, and we want to get to an f of B. Now we know the shape of f and b. We know that f of b is going to be a b and an x. And now we're going to try to solve that problem. So the first step is going to look at f of a, and we know that's a product, which allows us to use product elimination to get an a and an x. And now we have an a and a function from a to b, which means we get a b. And if we have a b and an x, we can then use product introduction to implement map. Right? We get an f of b, which means we have fully implemented map. And so here, there's no condition on f, a, or x. It always works. So for the rest of this talk, I'm going to keep using that a and x type because such a product is always a functor. Now we've not learned much yet. All we know about this product is that it's always a functor. but we're going to add more knowledge on that bit by bit for the rest of the presentation. Any question before I carry on?
No questions for the moment.
Okay, let's continue then. The next step, we're going to follow along the diagram I showed in the beginning. So the next step, once we have something that is a functor, is to find something that is a functor but not an apply, right? So basically solve this diagram. We start from something that is a type constructor and a functor, so the product type that we described. And we want it to not be an apply, which means to not have a map to function, where map to is useful in this circumstance. You have an f of A and an f of B, and you want to get to an f of C, but all you have to do that is a function from A and B to C. This is where map2 is useful, because then map2 allows you to take f, lift it, and produce a function map2 of f, which goes from f of A and f of B to f of C. So here map2 really is, the difference between map and map2 is map worked for a function that took one argument, but map2 allows you to work with functions that take two arguments. And if you have 1 and 2, then you can get 3, and then you can get 4, and you can get any number of parameters. So apply really is about applying functions that take multiple parameters. Right, so as I said, we want to start with something that is a functor, and we know of something that's a functor. It's our product, A and X. And we're going to try to implement map2 for it. So the diagram shifted around a little bit, but it's really the same one. It's just moved things to make room for all the nodes that I'm about to create. But it's still the same diagram. We still have our function from A and B to C, and we start from an f of A and f of B, and trying to get to an f of C. We know the shape of f of C. It's a C and an X, because it's a product. And, well, if we start from f of A and f of B, we know that we can use product elimination to get an f of A and an f of B. Now, the following is going to go just a little bit quick, but I'm going to slow down and explain after. But here we can use product elimination and product introduction at the same time to get both an x and x and an a and b. We get an x and x because f of A and f of B both contain an x. So we get these two x's by product elimination, and then we use product introduction to get an x and x. Similarly, we get an a and b. And if we have an a and b and a function from A and B to C, then we can get a C. And that's really already half of what we want to get. If we had an x as well, then we could get what we wanted. We don't have an x, we have an x and x. So really, what we need in order to actually solve the problem is some sort of function that I'm going to call combine that takes two x's and returns a single x. If you're familiar with these things, that basically means we want x to be a semigroup. And if you're not, being a semigroup means having a combined method, so it's convenient. And now, if we're going to pretend that x has this combined method, then we can go from x and x to x. We have an x and a c, which means by product introduction, we can finish implementing our map2 function. And this entire thing works because x has a combined function. So in order to break this, to understand how to take a counterexample, we would need to find some type that does not have a combined function. Now that can prove problematic because given any type x, I can always find at least two functions that, given two x's, return one, right? The first one, given two x's, I return the first x. Then the second one, given two x's, I return the second one. So from a structural perspective, any type is going to support a combined function, but it might not always make sense semantically. So to take an example, I suspect most of you are familiar with Jira, and if you're not, you probably are going to get familiar with it sooner or later. I'm terribly sorry for what's going to happen to you. It's not a pleasant experience, but think of it as a rite of passage. Right, but Jira, on top of being an abomination and a god, is a ticketing system. And it allows you, on tickets, to add labels. So for example, for a given ticket, you could have the label V1 to say that in order to release the first version of our software, we need this ticket to be finished. and a tag front-end, which tells us that this ticket is about something front-end, and somebody who has front-end skills should tackle it. And we would model this label as a string, right? So there's plenty of ways we could combine that. Again, taking the first or the second one, or we could concatenate them. But that wouldn't make any sense. If we have these two tags, v1 and front-end, we can't lose one. Both of them are important. Not one of them is not more important than the other. So if we lose information, we have a problem. And we can't concatenate them either, because front-end v1 or v1 front-end is not a thing that means anything. That's meaningless, right? So here, if we decide that x is going to be string, where here the string represents a label, there's not actually a way of writing the combine function for it. So we can't write the same combine function for it, which means we can't pool combine, which means we cannot produce the x that we need to create our f of c, which means we can't implement map2, which means we found a type that was not an apply. We just need to give it a name. Our f is the association of an a and a label. So we're going to call it labeled. It's a label, it's an a and a label. And then we have it. Labeled is a type constructor that is a functor, but not an apply. And what we've learned here is that one new piece of information is that a product is not an apply if the other member is not a semigroup. It doesn't have a combined function. Do we have any question before I carry on?
Yeah, HTML boy have a question.
Obviously.
How does not combining the static membrane invalidate apply in terms of laws? The applicative
So as I
laws.
said in the beginning of the talk, I'm going to be very hand-wavy. I'm not going to mention laws. I'm not going to talk about respecting the laws. This is going to be purely on intuition. Laws are extremely important, very useful, but I'm not going to talk about them yet. I'm not going to talk about them here because I'm not interested and I'm not qualified.
Okay. No other questions.
Okay. Now, next step, something that is an apply but not an applicative. So this diagram, right? Something that is a type constructor, so our product, and is an apply, so for which x is going to have a semigroup, but is not an applicative, which means doesn't have a pure function, where the pure function is useful in this scenario. We have an a, and we want to produce an f of a. Well, that's the entire purpose of pure. Pure takes an a and produces an f of a. And this can be useful in some circumstances. Imagine that you have a list of f of int, for example. So a list of int within some f, and you want to somehow get the sum of all these ints. Mostly, with the tools that we already have, it's very easy because we have map2 for apply. So you can just take the elements of this pairwise and just use map2 to lift plus into f and just sum everything. So that's going to work out. But what do you do if you have the empty list? Well, then you need to return f of 0, right? 0 within the f. And you can't do that because you have no way of going from an a to an f of a. So really, you need to have pure. Pure allows you to work with any number of variables, even 0. And yeah, that is what we're going to use pure for. Now, back to our product. Can we implement pure for our product? Well, we have an a. We're going to get to an f of a. And we know that the shape of f of a is an a and an x. And we do have an a, right? So we have half of the equation, but we don't have an x. So in order for us to be able to implement pure, we're going to have to add some more constraints on x. We're going to have to say x needs to have some sort of default value, which I'm going to call empty. Now again, if you're familiar with these things, you know that x is already a semigroup, and now it has an empty value. That makes it a monoid. Laws and everything, yes, but I'm not going to get bogged down in these details. And now if we have this empty value, then it's fairly straightforward to implement pure because we have an a and an x, which means we have an f of a. Right? So why does this work? This entire thing works because we have being able to write empty for x. So in order to break it, we need to take a concrete type for which it is impossible to write empty. An example I like to use for that is typically the weight represented as a positive int. Because here I'm going to pretend that it's impossible to have a weight of 0. And you can always combine weights by adding them. If you have two things that weight each something, and then you combine them together, then the weight is the sum of the weights. But you can't have something that doesn't have a weight. So it is possible to have combine. We still have a semigroup, so we still have f as an apply, but we can't implement empty. So we can't implement pure. So we can't make this type into an applicative. And as before, we're going to give a name to f. F is the association of an a and its weight. So we're going to call it weighted. And weighted is a good example of a data type that is an apply, but not an applicative. And we've learned one more thing. We've learned that a product is not an applicative if the other member is not a monoid, where monoid means combine plus empty. Do we have any question before I carry on to the more complicated parts?
No, not any question.
Good. All right, let's carry on. Now, I want to talk about something that's an apply but not a flat map. So here we want to work with something that a type constructor that is a functor or product and an apply where x is a semigroup, but not a flat map, which means doesn't have the flat map function. This flat map function is useful when you have, say, an f of a, and you want to get to an f of b, but all you have to go from one to the other is a function from a to f of b. In these circumstances, you can use FlatMap to create the function FlatMap of f, which then magically goes from f of a to f of b. And this function is very useful when you're trying to chain computations together, right? You have something that goes from a to f of b, then from b to f of c, then from c to f of d, etc. You can use FlatMap to produce f of a to f of b, to f of c, to f of d, combine the entire thing, and you get a function from f of a to f of d. So it's really about chaining computations. Now let's see how we can implement that for our product. Well, we have an f of a and a function from a to f of b, and we are trying to get an f of b. We know the structure of f of b. It is a b and an x. And the only thing we can start from is f of a, which by product elimination, we know how to get an a and an x. And we have an a and a function from a to f of b, which means we get an f of b. Now, you might think we've already we've already solved our problem because the goal is to get an f of b, and we have an f of b. But the problem here is this x that we've left on the side. It doesn't really do, right, to have part of the data that we had and just lose it all the time. So this is probably a hint that we're not doing something right. And we know that we have an f of a and an f of b, both of which contain an x. So we should probably try to combine these x's together at some point. So really what it is telling us is it is an f of b, but it's probably not the one we want. There's probably another one further down the line that we're interested in. And if we think about it that way, then we can use product elimination on f of b to get a new x and b, and that gives us an x and x. And since we said that what we were working with had to be an apply, then we know that x has a combined function. And since x has a combined function, we can get from these two x's to a single x. And now we have an x and a b, so we can use product introduction to get an f of b. And we now have implemented FlatMap for product. And this is a little bit confusing, right? Because we don't have any particular condition on any of the types that we're manipulating. So how are we going to break it? It seems impossible on the face of it. But, well, we're engineers. We like to break things, and we always find a way. So here, if we start from B and move backward, we need a B in order to solve this, right? Because without the B, we can't create an f of B. Well, we have that B because we could use product elimination on an f of B. We got an f of B because we were able to call f on an A. And we had an A because we were able to call product elimination on an f of A. And we were able to do that because f of A contains an A. What if it did not? Well, if we remove the A, then we can't get an A, which means we can't call f on that A, which means we can't get to the B. Basically, we break everything down. And we get to a type that cannot support FlatMap. So now, this f of A, we're going to need to try to find a concrete x to make it more understandable. And we know that the only constraint we have on x is that it's got to be a semigroup. So we've got to have a combined method. And we've already seen a type that has a combined method. We took positive int, right? That's a semigroup. So if we specialize x to positive int, then we can give a name to f of A. So now it's not exactly weighted, right? It's not a data associated with its weight. It's actually just a weight. So we're going to call it weight. And weight is an example of a data type, of a type constructor that is an apply, but that is not a flat map, which gives us an additional data point. A product is not a flat map if it's an apply with a phantom type. So phantom type is A here, right? It appears as a type. We have a weight of A, but it doesn't actually appear in the values. And I expect it's called phantom type because, I don't know, it's kind of spooky, I suppose. Before I carry on, do we have any questions?
No questions here.
Good.
Thank you.
Then finally, we're going to start talking about monads. So something that is an applicative but not a monad. We want a type constructor that is a functor, so our product, and an apply, so x has got to be a semigroup, and an applicative, so x has actually got to be a monoid. And on the other hand, in order to be a monad, an applicative has got to have a FlatMap function. So we want something that is an applicative but doesn't have a FlatMap function, and we know how to do that, right? We know how to make FlatMap impossible to implement. We just make the type parameter phantom. So in order to take this example, what we're going to do is we're going to take something that works and then remove the type. And a good example of something that works, so that's the product of an A with a type that has a monoid. And a monoid I quite like to use, very easy to use, is Boolean to represent a flag. And the flag, if it's set, then when you combine the flag with something else, you combine it with Boolean OR, and so it's always going to be set. So flag once set is never unset. And the default value for a flag is false, right? So we have the empty value and we have the combined function. If we use flagged as a type constructor, which is the product of an A and a Boolean, then we have the default value, so we can definitely implement pure by using false. And we can implement FlatMap, because all we need to implement FlatMap is to have a combined function. And as I said, we can use logical AND for that. So this works. Flagged is all the things we need, is a monad. And now we need to make it so that we can't implement FlatMap. And we know how to do that by making A phantom, or basically by removing A, because if we remove A, we can't implement FlatMap. But we can still implement pure, right? So we have a data constructor that is an applicative, but not a monad. And as before, this is not exactly flagged anymore because it doesn't associate a value with its flag. It's just a flag. So we're going to create flag. And there you have it, a data type that is an applicative, but not a monad. Now I'm going to say that we learned something more here, but that's not entirely true. We've learned that a product is not a monad if it's an applicative with a phantom type. But that's just taking two things we already knew and taking them together, right? There's no concrete new knowledge here. Do we have any questions?
No question on the chat, but just from my side, maybe it would be nice to talk about the constant functor, which is the kind of type constructor that you are mentioning.
The Watson.
The constant functor. I mean,
Right. Yes.
I know
So
that you are trying to succeeding in deriving of or type constructor from the product functor, but maybe telling that this is the constant functor.
I was very explicitly not naming the constant
Uh-huh.
function.
Okay.
No, but it's not it's good. It's just this is of course how I came up with this example.
Yeah.
I know that const is not a monad, so so this is exactly how I came up with the example.
Yeah. Okay.
I'm trying not to use too many scary things, or I'm just trying to give simple examples. But yes, of course, the general scenario, anything that is an applicative, any specialization of the const factor is going to be an applicative, not a monad. And a const factor is exactly what we've done, right?
Mm-hmm.
It's a type parameter, type constructor, where the type parameter is
It's a semigroup monoid. Yeah.
you only have a value in there. But yes, this is
Bo
absolutely
Boy is asking, is that really the phantom monoid? I don't know which is the phantom monoid.
I'm not going to answer that because that's going to be part of my conclusion.
Okay.
It's a very good question, which I prefer not to answer for the moment because I will answer it a little bit later. And if I have failed to answer it properly, then ask again, and then I'll try to do better tomorrow.
Okay, thank you.
Finally, the last step, something that is a FlatMap but not a monad. So that diagram really, where we start from something that is a functor, product, that is an apply, so X is a semigroup, that is a FlatMap, so A is not phantom, that is not a monad, so X is not a monoid. All the rules we've seen so far. And well, to break it, we're going to take a monad that we already know, right? We've already seen flagged, which is everything. And we're then going to break it so that the type we have here, Boolean, no longer has a monoid. So we're going to replace that with something that we already know, a semigroup, but not a monoid, weight as a positive int. Because weight as a positive int still has a combined method, addition. So we still can implement FlatMap, but we can't implement pure anymore because, well, false is not an integer, and there is no empty value we can use for positive int. The only value that would make sense is 0, but that's not a positive int. So we can't implement pure, and then we have a type constructor that is a FlatMap, but not a monad. And well, that's not called flagged because we're not working with a flag anymore. It's the association of an A and its weight. So it's a type we've already seen, right? It's weighted. Weighted is a type that is a FlatMap, but not a monad. And again, we've learned another data point, which is a product is not a monad if it is a FlatMap, but the other member is not a monoid. And with that last point, we've covered all the things I wanted to talk about tonight. Was it useful? That's certainly up for debate. If you look at the number of questions on the subject on Stack Overflow, people are certainly interested in it, but I'm not sure it's practically useful. I do think, however, that the way we've looked at the code here through diagrams, which we navigate by using rules such as composition, introduction, and elimination, it allows us to see things in a different perspective, such as, for example, the connection between applicative and monoids, which it's not something new. The original paper on applicative functors by McBride spends a fair amount of time spelling it out, but I never really got it, that part of the paper. But looking at the diagrams this way, when I was preparing the presentation, it actually made it click a little more than it used to for me. Now I see that connection a little bit more than I used to. And it's also an interesting way to look at monad, right? The monad requires a value to work with. So I think it's a different perspective on its sequential computations. We need the value in order to do the computation. So I quite like this perspective on monads. So I think maybe the data types I've shown you are not necessarily super useful in your day-to-day life, but I do think that this way of looking at the code can be interesting and bring some interesting insights. Now, if you agree with me, you can scan this QR code and get to the slides. And if you have any question, now is a good time to ask them.
Okay, thank you very much, Nicola. Some questions in the chat? Maybe you can answer the question from Boy about the phantom monoid.
Is that really the phantom monoid? Well, Javier already answered, right? He said it's not.
No.
So I didn't actually understand that he asked the phantom monoid. I don't know what the
a question from
is.
myself. Can you explain what is a phantom monoid?
I can't. So I hope that XHTML Boy can, because I can't explain what the phantom monoid is. I don't know what it is. I think it might be the first time I see that. Maybe we should check whether it's actually a thing. Big smile. Yes. As expected, we're being messed with.
Okay. So I like it very much from your presentation, the diagrams, okay, this
Cool.
way of explaining this. But I also really like it the step-by-step refinement of the implementation and how you get through the implementation whenever you can, and how you are blocked in the implementation in this step-by-step refinement. Sometimes you are blocked because you cannot proceed, you cannot go on. Okay, this I like it very much. The only thing is that there are times, for instance, when you are using specific types, okay, string, etc., in which you actually can proceed. And the only thing, because you can't actually get by with a right implementation, is because you are breaking the laws. Okay. So laws, you do not want to introduce laws, but maybe.
So now, if I had more than half an hour, this talk is supposed to run for half an hour. I think I massively underestimated how long it actually already took to go through. So I have half an hour. It's too much to talk about the laws. But out of curiosity, though, at what point in that presentation would I have needed to say, and we can't do that because this would not make it lawful? At what point do I need to bring in the laws?
Well, I think when you are working with the apply, I mean, when you are doing the first example for the apply, when you introduce the semi-group, and well,
I mean, I could have introduced the laws of semi-group, but the laws of semi-group are kind of boring, right?
Yeah.
Well, there is one law, and what is it again? It's associativity. I don't even remember. And they're not strictly required here.
No.
I mean, there's one point where clearly I jump through hoops in order to not talk about laws. It's the point where when we're doing FlatMap, and I'm ignoring, I say, well, we have an F of B, but that's not the one we want because we're forgetting an X. Yes, that bit is definitely my way of getting around the fact that if I said, well, we're breaking that monad law, that would make a lot more sense. And completely agreed, and that's absolutely true. It would make it more understandable, but that would add so much to the talk. Like, I have to present the laws, I have to explain what they are and how to use them. I only have half an hour. The point is very valid, but given the constraint of half an hour, I don't know how to work it in. If I can figure it out, I will, but I don't know how yet.
Yeah, maybe you're right. But still, I had to. I will go through your slide because I might be wrong, but it seemed to me that maybe it could be useful. But I will tell you.
I'm sorry. If you felt that I said it wouldn't be useful, I did not even mean to imply that. It would be useful.
Yeah, no, yes, but I would like to to answer your question, at which point exactly, okay, in this talk, it should be necessary to spell out the laws, because the signature that we have is a propositional signature. In order to introduce the laws, you cannot do that in the type system, in the Scala type system, okay?
I mean, at every step along the way, it would be useful to say, well, functor has its laws, and what we have done follows the laws. Applicative has some laws, and what we have done follows the laws. But so as far as I know, there's just this one point where I kind of cheat to not talk about laws, which is the point where we're trying to write FlatMap. At this point, I definitely, absolutely say, right, I would like to talk about the laws, but I'm not going to. So let's pretend that you understood why I did that. So this point, I really cheat. Definitely. If there's any other point where you feel like I'm cheating, I would love to hear about them, because I probably am cheating, but I'm not realizing it.
Okay. So some more questions.
Oh, right. Sorry. So the phantom monoid is just a fancy name for const. So definitely, then it was a phantom monoid, because as you said yourself, it was definitely exactly that. It was const. I was just taking some specializations of const. I did not know it was called a phantom monoid. That seemed like a weird name for it, but I'll look it up, and I've learned something tonight. Thank you very much. I do not know what he means by just a sock. So, but all right.
Just a sock associative. No. Okay.
Well, I mean, if this was a live session, I suppose we'd be headed out for a bar right about now, and I really wish we could do that. But yeah.
So the natural thing now would be to have some beers.
Yeah,
but that is not possible. So, okay. Let's see in Madrid. We will see, definitely. Okay, you will be here.
I'll definitely be in Madrid.
Okay.
I will be there for Scala Days. So at this point, we can definitely go out and have some drinks. I'd love that.
Sure. Okay. And the same goes for the attendees. Okay, thank you very much for attending. There will be a next meetup which is also sponsored by the Madrid Scala meetup group, also by Lambda World. It's a Lambda World meetup, actually. It will be here in Madrid. You are invited if you happen to be around Madrid. And okay, so again, thank you very much, Nicola. I hope it serves you. It serves you this little training. Okay.
And thank you very much for the feedback.
The talk is really nice. It is the kind of talk that I would have liked to hear some years ago when I started to learn this kind of things.
Okay. This is exactly what I'm aiming for. This is what I would have liked to see when I was learning. So thank you. This is exactly the kind of impression I'm trying to produce. I'm very happy that you said that.
Okay. Okay, so thank you very much. We are finishing the streaming. Okay.
See you later.
Bye. Bye, everybody.